All right, welcome back to MECH1320. All right, we are starting Chapter 3. This lecture is going to be in two separate videos, so we're going to do a couple different parts here. So this is the intro to Chapter 3. All right, we're just going to get started talking about, mechanical power and different, basic transmission fundamentals. So we're going to talk about energy, force, inertia, acceleration, friction, and work. Okay, so what does a mechanical system, consist of? It's very similar to what we talked about in the electrical course and things like that. It's got a prime mover, such as an electric motor or an internal combustion engine, wherein, electrical, we had, a battery, we had a power source, those sort of things. In mechanical, we have different components, right? We have shaft, gears, belts, joints, chains, different things like that, where, electrical, we had, different components like resistors, capacitors, inductors, those sort of things, different sensors, stuff like that. And then we have driven components in mechanical. So, we're turning a wheel or we're turning a conveyor or those type of things. Whereas, electrical, we're turning on a light or controlling, a motor or something along those lines. So you can still think about these across, all engineering type components, whether it's electrical, mechanical, fluid power. All the systems have the same kind of concepts, right? We're just changing what we're talking about with them. But, the fundamentals, like how you build the system, are relatively the same. So let's start talking about energy, okay? So energy has many different forms. There's kinetic, potential, heat, electrical, chemical, so on and so forth. Remember, kinetic energy is energy that's like in motion as it's happening. Potential energy, right? That's how much, like we might need inertia to get something going or something like that, right? Heat energy, we're burning, you're burning wood, you're burning coal. We turn that heat energy into something else, or we create steam and make an engine work, or those sort of things. We create, and those help create electrical energy and chemical energy, right? We have reactions. We make a battery, or we combine different compounds. All right, so those are all the kind of different forms of energies. So, main law of thermodynamics, right? Energy cannot be created nor destroyed. It just changes from one form to another. Okay, so that's really, the basics behind that piece. Basic units that we're going to talk about for energy: joules of energy, a foot-pound, just a way that, in the standard that we talk about a force, okay, foot-pounds, and then, how that relates to joules of energy. So 1 foot-pound is 1.356 joules of energy. Okay, we get into metric system, we're going to do stuff more in kilowatt hours. Okay, so kilo, right, remember, means 1,000. So 1,000 watts, or we can deem it into kilojoules if we convert it. So, it kind of depends on if we're imperial units, right, our standard stuff with feet and pounds and inches and that sort of thing, or we're in the metric system, we're talking about kilowatt and things like that. So like, in America, we talk about our truck's horsepower and things like that, but over in Europe, right, metric, we're talking about vehicles like kilowatt hours or kW, okay? So that's kind of how we're going to relate back and forth. And then, for us as humans, we burn calories. That's our energy and how everything relates. So those are just common units of energy that we go through. So let's talk about what a force is, okay? And, we're just reviewing basic physics in here. Some of you don't remember physics. Some of you may have never had physics or things like that. So this is just basic physics, okay? So a force, what's the definition for us? It causes an object that has a mass to change velocity. Okay, remember, velocity is like a speed. So we can talk about, a force to get something moving, where you have to push something to get it to actually start to go. Okay, or a force that's there and it stops something from moving. So, we have different ways. You're changing velocity, whether you're going from 0 to 60 or whether you're going 60 to 0. You're changing it. You're speeding it up or slowing it down or that sort of thing. So forces are, the way we define them, we define them in terms of vector. Vectors have direction and magnitude. So direction being positive or negative, right? Up or down, left or right, that sort of thing. And we deem that in terms of positive and negative. And it has a magnitude, so it has a value. So we're going to talk about newtons or foot-pounds or things like that, the units that are tied to what we're talking about. So a vector has magnitude and direction associated with it. So common units, right? Most common one that we'll use, right, is a Newton. All right, a Newton, and that's for our metric system. Okay, over here in the United States in our pure imperial system, right? We have a pound force, or what we call a foot pound. Okay, a foot pound is equal to 4.45 newtons. All right, let's talk about inertia now. Inertia, all right, by definition, is the resistance of an object to change in its motion state. But it's really like the amount of energy that we need to get something, to get it moving. All right, so if an object's at rest, how much inertia do we need to overcome to get it to actually get into motion? Okay, so let's take a look at an example here. We have object A that's 1 kilogram and object B that's 10 kilograms. Both of these we're going to act upon a 1 Newton force to the right, which would move at a higher acceleration, the 1 kilogram or the 10 kilogram. Well, think about it. How hard do I have to push to get that 1 kilogram versus that 10 kilogram object to get in motion? So obviously it makes sense, right, that the higher acceleration is obviously going to be that 1 kilogram force, because it doesn't weigh as much. So it's easier for us with 1 Newton of force to push it to get it to going than something that's 10 kilograms and to get it going. So how much force do you need to push your car versus a dump truck? Same kind of concept there. All right, so since object B has the larger inertia, right, it means more resistance to get it going, right? It has a higher resistance. It doesn't want to change its state. Objects at rest tend to want to stay at rest. So it's going to have a lower acceleration because it has more resistance. It's harder for us to push and get started. All right, so that brings us into Newton's laws of motion. So, okay, there's 3 basic laws of motion that Newton came up with. Okay, the first one we just talked about, the law of inertia. Okay, so what does that mean? By definition, right, a body at rest will stay at rest, and a body in motion will stay in motion unless acted upon by an external force, all right? If you set something down on the counter, like a glass or something like that, and you set it down, it's going to stay at rest, right? There's nothing that's making it move. It's just sitting there until what? You push it or slide it or something hits it, all right? Or you pick it back up, so it's going to stay at rest until you put it in motion, all right? Same with, your car. It's going to stay in motion if you're going down a hill unless you do something like press the brakes to slow it down or to make it stop. Okay, so objects in motion tend to stay in motion. Objects at rest tend to stay at rest unless acted upon by another force. Okay, so Newton's second law, that's the conservation of momentum. Very important one. You're going to spend a lot of time in physics doing this. F equals ma. Force equals mass times acceleration. So the net force acting on an object is equal to the rate of change of its momentum. Okay, so momentum is mass times acceleration. That's where we're getting for that. Okay, so F equals ma. And the third law is the action-reaction law. You've probably all heard these before because they're very common, right? But for every action, there's an equal and opposite reaction, or an equal in magnitude and opposite in direction. So, when you stand on the floor and you weigh 200 pounds, you're pushing down on the floor, but the floor's pushing up with 200 pounds of force to hold you up. So that's kind of how you think. Whatever force you push on something, right? At least to keep it in balance, all right? Now, if you swing a hammer or something like that, it kind of changes. But if you're just sitting there, equal and opposite reaction. So, if you set a glass of water on the table, right, one glass is 16 ounces of water or whatever, that table's got to push up with 16 ounces of force to keep the glass there so that the glass doesn't fall through the table, right? Yeah, paper obviously couldn't do that, right? You couldn't put a glass of water on a piece of paper. It's not strong enough necessarily to maintain that, or it might rip or tear sort of scenario, okay? So acceleration and deceleration, make sure you take notes on these. We're going to have an assignment on it where you've actually got to do problems that are just like these examples here. All right, so we're going to do some basic examples, some basic calculations. Okay, so the change of speed of a body. If speed decreases, then it's called a deceleration. okay? If speed increases, it's acceleration. So we have those two forms. Accelerating, we're increasing. Decelerating, we're decreasing speed. So when you're driving, right, and you're really pushing down on the gas, all right, we're accelerating. You ease off the gas, all right, we're decelerating because the car will slow back down. Okay, so we can understand and take some of these concepts using Newton's second law. Force equals mass times acceleration. Well, and you ask yourself, why are there little arrows over the F and the A? Okay, so, well, because that represents a vector. And we talked about before, a vector has both magnitude and direction. So anytime we have a little arrow over it in physics, or a little hat, or some sort of symbol or accent on top of the letter, we're denoting it as being a vector, okay, in this case. So let's take a look at this example here. We want to find what is the acceleration of object A if a force of 2 newtons acts upon it, or what is the acceleration of object B if a force of 20 newton acts upon it. So we're just going to apply F equals ma. So looking at object A, right, we're going to use a 2 newton force, and it's 1 kilogram. So F equals ma, but we're solving for acceleration, so that's 3 variable manipulation there. So we have to solve that equation for A, because we're looking for acceleration. So we have to divide both sides by m, it's mass, right? So force divided by mass equals acceleration. So I've got to take 2 divided by 1. All right, so that's going to tell me. And then for part B, right, or for question 2, object B, all right, we're going to take 20 divided by 10. That's going to give us our acceleration when we do this, okay? So, based on numbers, they can still have the same, right? It looks, deceiving. You would think that the acceleration of the larger object wouldn't be as great as the one of the smaller one, but when you actually, in fact, do the math, they have the same acceleration, okay? So, just make sure that we calculate everything correctly. So, force divided by mass is our acceleration. All right, another way to calculate acceleration is final speed minus initial speed, so change in speed or change in velocity over time. Change in velocity over time. Okay, so final speed minus initial speed, that's change in velocity, divided by time, okay, and that's going to be in meters per second squared. That's what our acceleration is. So let's do an example here. We have a vehicle moving at a speed of 20 feet per second. After 4 seconds, the vehicle is moving at a speed of 15 feet per second. What's the acceleration of the vehicle? So in this problem, we have to identify the vehicle's moving 20 feet per second. We have to decide, is that our final speed or our initial speed? So after 4 seconds, the vehicle was moving at a speed of 15 feet per second. So since it's after 4 seconds, that's our final speed. Okay, so don't automatically just say, oh, it's 20 minus 15. It's not, okay? Our initial speed is 20. Our final speed is 15. So you have to do 15 minus 20. Our time was 4 seconds divided by. It's important. It's okay if the answer comes out negative, because that tells us if we're accelerating, if it's positive, or we're decelerating if our answer is negative. So the sign does matter. Okay, so when we do this, it's going to be 15 minus 20 divided by 4. So we get negative 5/4. All right, we got feet per second over second. All right, and this is where we get second squared. So it's negative 1.25 feet per second squared, which means our acceleration is actually a deceleration. We're slowing down because the negative tells us that. If the answer was positive, we would be accelerating. Since the answer is negative, we are decelerating at a rate of 1.25 feet per second squared. Okay, so it's very, very important that we understand the vehicle is decelerating in this case, okay? You're going to have some homework problems just like this. You'll see this again on your test, so make sure that you understand those. Okay, angular speed, all right? So this is the speed of something rotating. Very important for motors, right? Those of you already in industry, or if we've worked on motors or things like that, we know that RPMs matter, revolutions per minute, how fast that shaft is spinning, all right? And that affects your vehicle as you do acceleration and give it more gas and less gas, right? It's how fast your wheels can spin. So that's what angular speed is. So how we measure that, right, is 360 degrees in a circle. That's why it's angular speed. It's circular motion, right, but there's 360 degrees in a circle, or 2 pi in a circle if we're using radians. So that's why it's important that we understand what angular speed is. Revolutions per minute, how fast an object can turn around. So, if you take like a disc and you put, a black dot on the end, and as it spins around, we're trying to keep track, of how fast that little black dot turns. So we use RPMs, which are revolution per minute, or we use rads per second, radians per second. Radians means we're doing something in terms of pi. All right, so you guys in your assignment, you're going to have to calculate surface velocity. Okay, all these equations are in chapter 3 in your book towards the end where the problems are as well. Okay, just so you know that they're in there. All right, so surface velocity in feet per minute. Remember, a velocity is always going to be a distance over time kind of scenario. There's two different ones here, right? There's RPM, revolutions per minute, times pi times diameter, and that's if it's in feet, or we can take RPM times 0.262 times diameter, and that'll give us our answer in inches. What happens is when we take pi divided by 12, right, because 1 foot there's 12 inches, so pi divided by 12 is the 0.262. That's where that value comes from. All right, it's doing the conversion for us with that. Okay, so example 4 says, what is the surface velocity of a 20-inch diameter rotor that rotates at 1,500 RPM? So important pieces here, right? We have the diameter, it's 20 inches, and we know that the rotor rotates at 1,500 RPM. So that's going to help us when we do the calculation. We have the RPM, we have the diameter, and we already have the conversion factor for everything. So all we really have to do is, I wrote down both versions here, the top one, RPM times pi times diameter times 1 foot 12 inches, or you could take RPM times the 0.262 times 20 and get the same answer. Okay, so revolutions per minute, 1,500 times 0.262. Remember that 0.262 comes from pi divided by 12, so that you end up in the correct units of feet instead of inches, times 20 inches. How did we know we have to do that? Well, because the diameter is in inches, and our velocity has to be in feet per minute. Does that make sense? So if we look at surface velocity here, it says we have to end up in feet per minute. Well, our diameter is given in inches, so that's how we have to know we got to convert inches to feet in order to get the right numerical value. Okay, so very important if we understand where that stuff comes from. All right, friction. All right, friction is what? It's what slows us down or makes it hard for us to push something. All right, so that's really what friction is. You want, friction when you're on a road so that you don't slip off. But it's the resistance to mechanical force, right? If you take your hands and you rub them together, you're creating friction. Friction produces heat, all right? So when you're rubbing two things together, you're producing heat. But it's resistance to mechanical force. How hard do you have to push and overcome that friction to make something roll or move? It applies to solids and fluids as well. Okay, so different types of frictions that we can talk about here. 3 main ones, right? Static friction, when the contacting surfaces are at rest. Okay, so say you take 2 things that are covered in like sandpaper that's got a really like rough grit on it. All right, it's going to be hard for you to move that because it's trying to grip. Or you take something that's rubber coated and you try and slide it across like a basketball floor. All right, it's really hard. Both of those contacting surfaces, if you start them at rest, it's not going to roll around too much, okay? But it's hard for you to overcome that friction, right? Because that rubber has a higher coefficient of friction than the floor, so it's going to stop you from trying to slide the ball or, slide your shoe when you're running and you want to stop. All right, there's sliding friction when one or both of the contacting surfaces are at motion. Okay, that's, I guess, what I was talking about with the last example. Static friction was what holds something in place. So when you set down like your mouse for your computer, like on a table, you set your laptop down, you set your book down, that's static friction because you set your book down and it doesn't just fall off the table, okay? Obviously that comes with your table being level and that sort of thing as well. Okay, and then rolling friction, when surfaces are separated by rollers, right? So we have something that's on casters and we're pushing it down the hallway, or those kind of things, okay? So main types of friction right there. So we always quantify friction, and I said it a little bit earlier, right, by the coefficient of friction. So some things have a high coefficient of friction, some things have a low coefficient of friction, all right? And that's where we bring into account, we'll start talking about lubrication and things like that a little bit later on. It helps reduce friction and wear and tear. Okay, so let's talk about work. Work equals force times distance. Most of you guys have probably, talked about work or heard of it, okay? And the units for work are Newton meter or foot pound. We've mentioned foot pound, a lot. So let's do another example here. A force of 10 foot-pounds, okay, is applied on a body at rest that has a mass of 4 pounds. Then the force was removed after the body moved 5 feet, okay? So we want to find out how much work was done. So our force is 10 feet, okay? And then, right, the body at rest has a mass of 4 pounds. What do we have to calculate here? I need you to start thinking about some things, because not all the equation might be here, right? Remember, there's another way for force, because right now we got force, we've got mass, and we have our distance. Our distance is 5 feet, so that's good. So we have to actually, calculate something else with force, to get our work when we do this, okay? So this is really what we're doing. We're taking a 10 Newton force on a 4 kilogram. Sorry, my picture doesn't match. I changed it to pounds because I wanted to be in standard. So assuming we have a 10 foot-pound force, when I use the animation, and a 4 pound force here. Either or. Numerically, it's the same whether I'm using newtons or kilograms here. Biggest thing, though, what's the acceleration? This is the most important part we got to do to finish the problem here, right? Remember from before, F equals ma, force equals mass times acceleration. Therefore, acceleration equals force divided by mass, right? Just doing 3-variable algebra manipulation there, okay? So as I kind of show you here on the screen, so we're going to take 10 divided by 4, and we get 2.5 feet per second squared. Make sure you're keeping track of correct units. Acceleration is feet per second squared, so very important here. We want to find the work performed on the body here. Work is just force times distance. We know the force. We know the distance, so it's 10 times 5. 10 is the force, 5 is the distance, so it's 50 foot-pounds when we do that calculation. All right, so let's just do some examples here or exercises so we kind of understand. We want to know which of the following are vectors and which are scalars, okay? Remember, a vector is something that has both magnitude and direction. A scalar is just kind of a multiplier type value and things like that. So if we look at temperature, temperature is a scalar. Doesn't necessarily have to have a magnitude and a direction. It really just has kind of a magnitude. It's kind of a value, okay? If we have pressure, pressure is a scalar, okay? It's just a value that we have in pressure, okay? Think of a vector as the units have to have 2 parts. So if we look at temperature, temperature has what? It's Fahrenheit, Celsius, Kelvin, Rankine, okay? That's what temperature is. It's a scalar. It only has 1 unit tied to it. Same with pressure, right? Pounds per square inch, right? Our PSI of pressure. So that one has multiple, but it's just a scalar, all right? When we talk about PSI, it's one kind of way that we do it, okay? Where velocity, okay, has a magnitude and a direction, okay? So velocity is going to be a vector, okay? Because what's the direction, right? We're speeding up, or we're speeding down, or slowing down, or decelerate. I'm not going to say deceleration because that's with acceleration. We're either speeding up or speeding down, and we give that by what? A negative number in front of it, right? So that's why, right? When something's dropping, to the earth, because of gravity, gravity's negative there because it's dropping down, okay? Acceleration, also a vector, okay?
Energy, just a scalar. Okay, force is a vector, right, because it's mass times acceleration. And if acceleration is a vector, force has to be a vector, right? Okay, and then inertia is just a scalar. So you can kind of break it down and understand the units as you get through these. All right, so let's match these, just based on stuff that I've talked about, the correct unit to its measurements, okay, or to its term. So when we talk about mass, which one of these, seems to fit the best when you do this? So what you might want to do is pause the video and go through it, and then I'll kind of see if you're right, okay, and then I'll go through it. All right, so mass for us is kilograms or pounds, right, if we're over here in the U.S. Energy, okay, energy, very important. A kilowatt hour is energy, okay, kilowatt hour is energy. A velocity, careful, don't get velocity and acceleration mixed up. Velocity is just a rate, right, a distance over time, so that would be feet per second here, okay. Acceleration, it's distance over time squared, so in this case we're talking meters per second squared. Force, okay, think of mass times acceleration, so you're looking for, some sort of, unit that goes with that, but we've talked about force plenty of times, and we know that it's just going to be a Newton or a foot-pound, okay? Power, this goes back to electrical, right? Power, kilowatt, okay? So make sure we understand kind of the difference between energy and power. Energy is what? Like, power over time sort of rating, okay? That's why when you pay your energy bill or your electric bill, it's in kilowatt hours, okay? You're using a certain amount of power over time, and that's what they're charging you for. And then angular speed, last one left anyways, but revolutions per minute. How many times does it go around a circle, right, in a minute type thing? So, all right, well, that's the end of the first part of Chapter 3 lecture. So email me if you got any questions or let me know. Else, you're going to have a nice worksheet to help you review some of the problems we went over, and that will be on your quiz as well. So, else, guys, have a great day. I'll see you in class.